What if humanity's true origin lies not here on Earth, but millions of miles away under a red sky? What if we are the descendants of a civilization that thrived on Mars long before our planet ever knew life? Stay with me until the end, because the evidence we're about to explore could fundamentally change not only how we see Mars, but how we understand the very origins of human existence. If explorations like this fascinate you, subscribe to the channel. Every video here carefully unfolds forgotten history, lost civilizations, and mysteries that lie beyond accepted theories. Your support helps continue this journey. Mars has always been a planet of mystery, but in recent years, it has transformed from a simple object of curiosity into a place where real scientific data forces us to reconsider its past. For a long time, Mars was considered nothing more than a cold desert, a dead world of rock and dust. When telescopes became more sophisticated, people noticed faint markings, white polar caps, and shadows that changed with the seasons. Early astronomers built hypotheses about canals and civilizations, ideas that were eventually dismissed as illusions. For decades, Mars was again perceived as a barren planet full of craters and rocks. But the picture has changed. Modern spacecraft, rovers, and orbital stations have shown us a Mars that is far more complex than we imagined. This is no longer a dead planet. This is a place that once bore the same conditions that allowed life to emerge on Earth. Over the past decades, the most astonishing discoveries have come not from imagination, but from data. High-resolution images from orbit show valleys carved by flowing water. Rover missions have revealed layers of sedimentary rock that could only have formed in lakes. Minerals like clay and sulfates have been found in rocks formed in the presence of liquid water. These findings are consistent and repeatable. They tell us that Mars was not always the dry and frozen place we see it as now. Billions of years ago, it was warmer, wetter, and likely habitable. For some scientists, the evidence of habitability is so compelling that debates no longer center on whether Mars could support life, but on whether it actually existed. This gradual shift in thinking has opened new directions for contemplation. If Mars had water, chemistry, and stability over millions of years, then microbial life is quite plausible. But life rarely stops at microbes when conditions remain favorable. On Earth, it was only a matter of time before complexity emerged. Over 1 billion years, simple organisms became multicellular. Ecosystems spread across oceans and land, and eventually intelligence and civilization appeared. If Mars followed a similar timeline even partially, it could have seen its own version of progress. The intriguing part of this discussion is that Mars may have been habitable not in one era alone. Research into its climatic history shows that the planet may have gone through cycles, alternating relatively stable periods with long declines. Some models indicate that Mars could have had several windows when liquid water could exist on the surface. Each of these windows could have lasted millions of years. If so, life could have had more than one chance to emerge, disappear, and perhaps even restart in new forms. Civilizations, if they ever appeared, may not have been singular events but parts of repeating cycles separated by long epochs of decline. We are accustomed to thinking of civilizations only in human terms, but Earth's history reminds us how much can be forgotten. Ancient cities were swallowed by deserts, jungles, and oceans. Even our greatest monuments are vulnerable to time. If Mars had civilizations billions of years ago, almost everything we would expect to find could have been erased. What remains visible today may be only the faintest traces, geological scars that are difficult to distinguish from natural formations. And yet, the growing body of evidence that Mars was once habitable makes it harder to dismiss this possibility. The more missions we send, the clearer the picture becomes. The Curiosity and Perseverance rovers are not only confirming the presence of water in the past, but also detecting organic molecules, the raw materials for life. While this does not prove that life existed, it strengthens the argument that Mars was a place where it could have thrived. Instruments have detected methane in the atmosphere, sometimes giving spikes that remain unexplained. On Earth, methane is often associated with biological activity, though though geological processes can also produce it. The fact that Mars still shows activity today, even in small signals like methane, suggests that the story of its past may not be finished. The fascination lies in how these scientific findings connect to the larger question of civilization. It is one thing to imagine microbes or algae on Mars. It is quite another to envision societies, cultures, and technologies arising under its red sky. But once we understand that Mars was once habitable, the step to imagining civilization becomes not unreasonable. By ordinary standards, it may be unlikely, but it cannot be ruled out. The evidence has shifted the discussion from impossible to open. Particularly compelling is how Mars's history intersects with Earth's history billions of years ago. Mars may have been habitable earlier than Earth. If so, then life could have started there first. Civilizations, if they formed, could have arisen before Earth had even stabilized as a planet capable of supporting life. This idea is profound. It suggests that humanity may not be the first intelligent species in the solar system, but simply the most recent. Our history may be younger, while Mars holds more ancient chapters erased by time. This perspective changes our approach to exploration. Missions to Mars are no longer aimed at finding a completely lifeless planet. They are searching for traces, even subtle ones, of a world that once may have contained much more. The more evidence we gather, the more plausible it seems that we are missing pieces of a much larger story. Mars has transformed from a distant object in the sky into a possible cradle of civilizations older than our own. Every rock sample, every radar scan, every atmospheric measurement is not just data. It is a clue in an unfolding mystery. Here it is important to maintain caution. Speculation should not be mistaken for evidence. At present, there is no confirmed evidence of civilization on Mars. The ruins we imagine are, for now, products of human curiosity. But curiosity itself is not without value. It prompts us to ask questions that science may eventually answer. For centuries, people believed that Earth was the only world that mattered. Then we learned it was just one planet among billions. We believed life was unique until we saw that the chemistry of life exists everywhere. Mars is the next step in this process. What we find there may change our view of our place in the universe. As new missions prepare to bring samples back to Earth, we may be closer than ever to answers. If these samples show signs of biology, then the leap to imagining more complex histories on Mars becomes harder to ignore. Civilization may remain speculation, but the chain of evidence, water, habitability, chemistry, and geology, continues to push the boundaries of what is possible. Mars is no longer just a barren planet. It is a mirror held up to Earth, showing us how fragile habitability can be, and how easily civilizations, if they ever existed, can be erased. Here the discussion opens further. If Mars truly had these periods of habitability, if it was stable enough for civilizations to emerge, what happened to them? Did they vanish as rivers dried and the atmosphere collapsed? Did they retreat underground, hiding in lava tubes where survival was still possible? Or did they leave, seeking new worlds when their own could no longer support them? These are questions that naturally follow from the evidence we already have. When scientists look at Mars's past, one of the most intriguing discoveries is that the planet may have had not one period of habitability, but several. Instead, it appears Mars went through cycles. For millions of years, the climate could warm, the atmosphere could thicken, and liquid water could be stable on the surface. Then, gradually, the planet would cool, its atmosphere would thin, and the surface would freeze. After long periods of decline, conditions could improve again. This pattern suggests that Mars may have had multiple windows of opportunity where life, and possibly civilizations, could appear. On Earth, life has survived mass extinctions, ice ages, and catastrophic collisions. Yet it always found a way back. Mars could have followed a similar path, though on a different scale. The presence of ancient riverbeds, deltas, and lake basins indicates not just one moment of habitability, but several. Some regions show evidence of repeated flooding, drying, and flooding again. These cycles could have created environments where life had more than one chance to begin and evolve. If civilizations ever existed there, they too could have risen, collapsed, and disappeared in response to these cycles. The idea of multiple windows of habitability raises questions about resilience. If life emerged on Mars during one of its early warm periods, could it have survived long enough to adapt to the next? On Earth, life has shown remarkable ability to survive in extreme conditions. Bacteria thrive in deep oceans, inside rocks, and even in radioactive waste. Mars could have contained equally resilient forms of life, retreating underground or into protected environments during harsher times. If civilizations grew from such life, they may have developed a culture deeply connected to cycles of survival, migration, and adaptation. It is not hard to imagine how such cycles would shape a civilization. Picture a society that thrives in a warm period, building settlements near rivers and fertile valleys. Generations may prosper, creating culture, technology, and traditions. Then, as the climate shifts, these rivers dry up and the land becomes uninhabitable. The civilization may collapse, its people forced to retreat into caves, underground shelters, or smaller isolated regions where survival is still possible. Over time, knowledge is lost, traditions fade, and ruins are swallowed by dust. Thousands or millions of years later, the cycle turns again and new opportunities emerge. Perhaps a new civilization grows, unaware that it is not the first to walk the Martian plains. These cycles could explain why clear evidence of civilization is so hard to find today. Each window of habitability could have left traces, but the long declines between them would have erased most signs. Surface structures would have collapsed, artifacts would have been buried, and only the most protected remains could endure. Lava tubes, caves, and subsurface vaults could be the only places where faint remnants survive. Discovering them would require searching beneath the surface, something our current missions have only begun to explore. The possibility of repeating cycles also deepens the question of timeframes. If Mars had multiple chances for life and civilizations to develop, some could have occurred billions of years before Earth was ready. Our planet took time to stabilize, oceans had to form, the crust had to cool, and the atmosphere had to reach balance. Mars could have been habitable earlier. If civilizations appeared in those early windows, they could have had an enormous head start over anything that developed here. It is a strange thought that intelligent beings could have walked under Martian skies while Earth was still a world of molten rock and toxic air. Even if civilizations did not survive the long declines, memory of their existence would remain in the form of faint geological and chemical markers. Perhaps fragments of tools or structures remain buried under layers of rock. Perhaps cultural attempts to preserve knowledge still exist, waiting in underground chambers. These ideas are speculative, but they naturally follow from what we already know: that Mars was habitable, that it had cycles of stability, and that there was enough time for life to have multiple chances to develop. It is also possible that civilizations on Mars, if they existed, could have understood these cycles better than we do. They may have watched the slow decline of their atmosphere, the drying of rivers, and the cooling of their world. Their myths and traditions could have reflected a deep awareness of planetary changes. Some cultures may have prepared, retreating underground or seeking ways to adapt. Others may have collapsed suddenly, caught off guard by changes too rapid for survival. If any knowledge of these cycles was ever preserved, it could be hidden in symbols, carvings, or structures aligned with astronomical events, left as a warning for future generations or perhaps for other worlds. What is remarkable is that this story is not entirely alien to us. On Earth, we too have seen civilizations rise and fall in response to climate change. The Akkadian Empire collapsed during a period of severe drought. The Maya civilization declined after centuries of ecological stress. Ancient cultures in the Sahara were erased when the desert expanded. If these patterns occurred here in just a few thousand years, it is easy to imagine that over billions of years, Mars could have seen similar cycles repeating many times. The challenge is that Mars's cycles operated on scales far longer than human history. Civilizations could have come and gone over millions of years, their traces eroded beyond recognition. To find them, we need to think differently about evidence. Instead of searching for whole ruins, we may have to look for anomalies in geology, subtle signs suggesting human-like activity, but unexplainable by natural processes alone. This is a difficult task because erosion and time blur the boundaries between natural and artificial. But it is not impossible. Every new mission brings us closer to identifying faint signals of a deeper history hidden in the Martian soil. If civilizations rose and fell with each cycle, this changes how we imagine Mars. It is not simply a planet that once lost its habitability, but a place that could have lived, died, and lived again many times. Civilizations, if they existed, may not have been singular. They could have been part of a repeating rhythm, echoes across vast spans of time. In this sense, Mars is not just a world of silence. It is a world of forgotten stories, layered upon one another, waiting for us to uncover them. This brings us to a deeper question. If there were cycles of habitability, and if civilization had multiple opportunities to rise, where would the best evidence of their existence survive today? The surface is hostile, eroded, and bombarded by radiation. The underground, however, could hold secrets untouched for billions of years. Lava tubes, caverns, and deep shelters may have not only preserved traces of life, but traces of civilizations that understood their world was fading and sought refuge below. If civilizations on Mars ever retreated underground, then the planet's geology would have played a substantial role in shaping their lives. Mars is not simply a desert world of dust and stone. It is also a planet of volcanoes, canyons, and vast subsurface networks formed by ancient geological forces. Among these features, lava tubes stand out as some of the most promising environments for both survival and preservation. These enormous natural tunnels, created when rivers of lava once flowed across the planet, can extend for miles beneath the surface. They are so large that some could house entire skyscrapers inside. For a civilization seeking refuge, they would be ready-made shelters, protection from radiation, stable in temperature, and large enough to support entire communities. On Earth, lava tubes also exist, but they are modest in size compared to Martian ones. Mars's lower gravity means that tunnels could form on a scale far larger than anything we see here. Some radar scans from orbit suggest the presence of collapsed skylights that may lead into hollow spaces extending for kilometers. These environments would provide more than just safety. They would offer the opportunity to build a settlement with relatively little effort. Instead of constructing cities above ground, exposed to storms, civilizations could expand into natural caverns, transforming them into habitable environments. Mars's geology also contains other features that could have been used for shelter. Canyons like Valles Marineris, the largest in the solar system, are dotted with cliffs and caves. Subsurface ice deposits may conceal aquifers, providing a potential source of water. Volcanic regions like Tharsis and Elysium contain not only lava tubes, but geothermal heat that could have been harnessed as energy. If civilizations existed, they would have had access to diverse natural resources hidden beneath the surface. Mars's underground may not have been a place of scarcity, but a place of opportunity. Life in such conditions would have required adaptation. For a civilization confined to lava tubes and caverns, light would be the first challenge. Sunlight does not penetrate far underground, so artificial lighting would be necessary. On Earth, ancient humans used torches and lamps, but over time, more advanced solutions emerged. On Mars, civilizations might have used luminescent minerals, chemical reactions, or even bioluminescent organisms if such life existed. How they illuminated their world would have shaped their culture and aesthetics. Their art, architecture, and technologies may have been designed around enclosed spaces filled with artificial light rather than open skies. Air circulation would be another challenge. In closed spaces, ventilation is essential to prevent the buildup of harmful gases. Civilizations on Mars could have engineered ventilation shafts, fans, or natural airflow systems. If they had advanced knowledge of geology, they could choose locations where airflow was naturally possible. This would require careful planning, suggesting that Martian societies could have had deep understanding of their environment. The size of lava tubes suggests that entire cities could have been housed within them. Imagine vast chambers carved into rock with walls smoothed and decorated, ceilings glowing with artificial light, and floors divided into living quarters, gathering places, and storage areas. These underground cities may not resemble our surface settlements, but they could be no less sophisticated. To outsiders, such spaces might seem alien and difficult to interpret. But for those who lived there, they would be normal, comfortable, and protected. One of the most intriguing aspects of using lava tubes is their potential for preserving history. On Mars's surface, radiation erases organic molecules, erosion destroys structures, and impacts scatter debris. Underground, conditions are stable. If civilizations ever left carvings, tools, or even bodies, they could exist today, waiting for discovery. Stone carvings inside a lava tube could look as fresh today as they did millions of years ago. The underground could be a time capsule, holding secrets that the surface has long erased. We can also imagine that civilizations may have intentionally used these spaces as archives. If they knew their world was in decline, they could have placed records, artifacts, or cultural treasures inside caverns, believing the underground would protect them. On Earth, caves have preserved art and artifacts for tens of thousands of years. On Mars, where geological activity is slower, preservation time could be far longer. The underground could be not only a place of survival, but a place of memory, a way for a civilization to leave something behind, even as their world faded. It is worth considering how such underground environments would shape culture itself. A society living in caverns would see the world differently. Their mythology might focus less on the sky and more on the earth beneath them. Their architecture would be directed inward, designed for protection and efficiency rather than external display. Their technologies would prioritize survival in enclosed environments. Their art might emphasize glowing light, shadows, and stone. If such a civilization ever left traces, we might recognize them not through grand above-ground monuments, but through subtle signs carved deep below. Mars's geology provides clues that this is not just an imaginative exercise. We already know lava tubes exist. We know caves and caverns can be found throughout the planet. And we know underground water may still be present. These facts make the underground one of the most promising places to search for life. Future missions may send drones to fly through lava tubes, scanning walls and floors for unusual patterns. Human explorers may enter caverns that have remained untouched for billions of years. What they find there could redefine our understanding of Mars. It is possible that when we finally explore these underground spaces, we may find them empty. They may be silent, filled only with rock and dust. But even that would not end the story. Absence of evidence is still evidence of possibility. Just knowing that such environments exist deepens the argument that Mars could have supported civilizations. It shows us that the planet had not only surface conditions, but also protective shelters where life could endure longer than we thought. This is why underground environments are so important to the discussion of Martian civilizations. They offer both a survival strategy and a preservation system. If civilizations ever existed, the underground is where we are most likely to find them. And if we do find them, what we discover may not look familiar. Mars's geology shaped its underground in ways that are alien to us. Civilizations there could have looked and lived in ways we can barely imagine. But that unfamiliarity is part of what makes the question so compelling. If we find nothing, Mars remains a lesson in planetary fragility. If we find something, even the faintest trace of civilization hidden in lava tubes or caverns, it changes everything. It means Earth was not the first cradle of civilization in the solar system. It means human history is only a continuation of something more ancient, something that began under the red sky of Mars and was preserved in its silent underground. The thought that civilizations could have lived in caverns, creating entire cultures in shadows, naturally leads to another question. If they existed, would they have looked or thought like us? Or would the unique pressures of Mars, the underground, the thin atmosphere, the alien environment have shaped them into something entirely different? When we think of civilizations, we usually picture them in human terms. Cities with streets and buildings, tools made of metal, and social structures resembling our own. But if Mars ever hosted civilizations, it is unlikely they would resemble anything familiar. Different environments produce different solutions. On Earth, human society was shaped by sunlight, abundant water, fertile soil, and a protective atmosphere. Mars offered none of these conditions in the long term. Its civilizations, if they existed, would have been shaped by scarcity, radiation, cold, and confinement. They might not look like us, think like us, or build like us. Their way of life could be alien in the truest sense of the word. Mars's surface environment is dominated by extremes. Temperatures swing wildly from far below freezing at night to slightly above during the day. The air is too thin to breathe, and radiation penetrates the ground. Above all, liquid water is unstable on the surface. These factors would force civilizations to adapt in ways unfamiliar to us. We build outward under open skies. Martian societies might build inward, beneath rock and soil. They might not have grand monuments rising above the ground. Instead, their architecture could be hidden, carved into cliffs, caves, and lava tubes. From orbit, their presence might look like nothing more than natural geology. Technologies, too, would follow different paths. On Earth, agriculture thrived in river valleys under sunlight. On Mars, farming would require enclosed spaces, artificial light, and constant recycling of resources. Instead of broad fields, Martian civilizations might grow food in underground chambers, using chemical processes to power plants, or perhaps even cultivating organisms we would not recognize as crops. Their entire food system could be compact, efficient, and hidden from view, designed not for expansion, but for survival. Energy is another area where differences would be evident. On Earth, civilizations used fire, wind, water, and eventually fossil fuels. On Mars, with its thin atmosphere and limited resources, fire would be less useful, wind less reliable, and fossil fuels possibly non-existent. Civilizations might rely on geothermal energy, using volcanic heat beneath the surface. They might develop systems of chemical energy, exploiting minerals and reactions available in Martian geology. If so, their tools and machines might not resemble ours. They could look strange, built from materials unfamiliar to us, leaving traces we might mistake for natural formations. Even their sense of time could be different. A Martian day is close to an Earth day, but its year is nearly twice as long. Seasons last longer, and climate shifts occur over geological timescales. A civilization accustomed to such rhythms might perceive time differently than we do. Their generations might plan for slower changes, their traditions rooted in cycles of scarcity and recovery. Survival in such an environment might require patience, resilience, and cultural memory far deeper than ours. If civilizations existed underground, their very bodies might have adapted to such conditions. Without sunlight, skin tones could be pale or covered with protective layers. Without abundant resources, growth might be smaller, designed for efficiency rather than strength. With limited light, vision might be sharper in darkness. This is speculation, but it follows the logic of adaptation. Civilizations on Mars might look different not only in their culture but in their biology. Their physical forms could be shaped by the demands of caves, scarcity, and survival. This also raises the question of communication and expression. On Earth, art is often displayed on walls, monuments, and open spaces. In underground societies, art could be carved into stones, glowing in dim chambers, or encoded in patterns visible only under certain light. Sound might travel differently in enclosed spaces, leading to unique forms of music, chanting, or communication. Language itself might evolve differently, shaped by echoes, whispers, and the acoustics of stone halls. Culture would grow in directions alien to us, yet still reflecting intelligence and creativity. We must also consider how their sense of space would be shaped. Humanity developed astronomy by watching the heavens. Martian civilizations living underground might see the stars less frequently. Their awareness of space could be rooted in stories, myths, or rare observations through skylights and openings in caves. When they looked up, they saw Earth as a bright star in the sky. Perhaps it became a symbol of hope, a reminder of another world nearby that seemed more stable and fertile. For a civilization facing decline, Earth could be a constant presence, inspiring legends or even dreams of migration. The absence of familiar ruins on Mars does not mean civilizations never existed. It may simply mean they looked different. On Earth, we expect stone walls, statues, and temples. On Mars, ruins may be indistinguishable from caves or rock formations. Tools and artifacts may be corroded or hidden within geology. Without context, they might be overlooked as ordinary stones. The challenge is not only to find evidence, but to recognize it when we see it. Martian civilizations may not have left behind the kinds of traces we know how to interpret. Their history may remain invisible until we learn to see with new eyes. This perspective also changes how we think about intelligence itself. On Earth, we assume civilizations naturally build outward, expand, and dominate their environment. But on Mars, intelligence could have taken a different path. It might focus inward, valuing preservation, efficiency, and endurance. A Martian civilization might not strive for expansion at all, but simply for survival. To us, this may seem modest, but in their context, it could be the highest possible achievement. If such societies existed, their intelligence would not be measured by skyscrapers or empires, but by how long they endured in a hostile world. The possibility that civilizations on Mars did not look like ours is humbling. It reminds us that human history is not the only template. Civilizations are shaped by their environments. Mars was a world of scarcity, cold, and decline. Its civilizations, if they ever existed, would be different in form, culture, and technology. They may be unrecognizable at first, but that does not mean they were not real. And this leads us to an important thought. If civilizations existed, and if they adapted in such unique ways, how would they try to leave evidence of their existence? Would they carve monuments, store records, or attempt to communicate across time? Or would their traces be so alien that we have already seen them without realizing what they were? If civilizations ever existed on Mars, it is reasonable to ask how they might have tried to preserve their memory. On Earth, cultures have always left signs of their presence, from cave paintings and stone tools to great monuments like pyramids and temples. We create markers to be remembered. Perhaps Martian civilizations, facing the decline of their world, also sought to leave signals, monuments, or records that could endure time. The difficulty is that billions of years have passed since Mars was stable, and the planet has endured erosion, impacts, and radiation. What traces could survive such scales of time, and would we recognize them at all if we found them? When we think of signals across time, we often picture large and enduring structures. Earth's pyramids, megaliths, and stone cities have lasted thousands of years. But even these structures are fragile compared to geological time. A few thousand years is nothing compared to billions. If Martian civilizations tried to leave monuments on the surface, the forces of erosion and dust storms would eventually erase them. Today, what may remain are only faint outlines, barely distinguishable from natural formations. This is why features like the so-called face on Mars continue to attract attention. While most scientists explain it as a natural mesa shaped by light and shadow, it reflects our tendency to wonder. Could civilizations have left markers carved into landscapes? The challenge is that erosion can create patterns that mimic intentional design, making it hard to separate natural from artificial. Another possibility is that civilizations might choose durability over grandeur. Instead of building massive structures, they could leave smaller, simpler markers in protected environments. On Earth, carvings in caves have lasted tens of thousands of years. On Mars, Similar carvings could endure far longer, protected from erosion and radiation. If Martian civilizations carved their stories into walls deep inside lava tubes or caverns, these records could still exist, waiting for discovery. They would not be visible from orbit. They would require exploration of the underground. But if found, they could provide direct evidence of culture, thought, and intention. There is also the possibility that civilizations left technological signals. On Earth, we imagine sending messages into space, radio waves, satellites, or physical artifacts designed to outlast us. Martian civilizations might have attempted something similar. Perhaps they launched signals into orbit, or buried artifacts designed for discovery by future generations or other worlds. Over billions of years, such signals could have degraded, but it is not impossible that fragments remain. Some unusual metallic anomalies detected on Mars have been explained geologically, but without detailed examination, it is hard to rule out other possibilities. If civilizations tried to communicate across time, they might also choose symbolism. They could align structures with astronomical events, ensuring their orientation remains recognizable even if structures erode. On Earth, we see this in places like Stonehenge, where alignment with solstices and stars endures long after the culture that built them vanished. On Mars, similar alignments could exist, perhaps in the positioning of mounds, ridges, or formations that seem too regular to be natural. To identify such patterns, we would need to map the planet in detail, looking not only for isolated anomalies, but for alignments across distances. It is also possible that civilizations, understanding the fragility of physical records, might choose to encode information in ways we do not yet understand. Just as humans use mathematics and geometry as universal languages, Martian civilizations could have left patterns based on numbers, ratios, or cosmic constants. These patterns could be engraved in landscapes, buried in structures, or embedded in artifacts. The difficulty is in recognition. Without context, we may dismiss them as random geology. Only by approaching Mars with scientific rigor and openness to possibility can we hope to interpret such signals correctly. One of the most profound challenges is that we may have already seen evidence without realizing it. Images from orbiters and rovers capture thousands of features. Most are cataloged as rocks, ridges, or natural formations. Among them could be traces of design, overlooked because they do not match our expectations of civilization. On Earth, archaeologists often reclassify sites once thought natural as artificial when context is found. The same could be true for Mars. What we now call geology may one day be reconsidered as archaeology. We must also consider the motivations for leaving signals for a civilization facing extinction. The desire to be remembered is powerful. They may have known their world was dying, that their atmosphere was vanishing, and that survival was uncertain. In such a moment, leaving a record becomes a way to continue existing, even if only symbolically. Their signals may not have been intended for us, but for their own descendants, or even for themselves, if they survived underground or migrated elsewhere. For them, memory could be as important as survival. If Martian civilizations left signals, then their discovery would not only confirm their existence but reveal their values. Were they focused on knowledge, leaving scientific records of their world? Were they spiritual, carving symbols of faith into stone? Were they practical, leaving instructions for survival in a hostile climate? Each possibility opens a different window into who they were and how they saw themselves. This brings us to an important realization. The search for signals from Martian civilizations is not only about finding monuments or artifacts. It is about learning to see differently. Our eyes are trained by Earth's history, but Mars may require new ways of interpretation. Its civilizations, if they existed, may have left traces that do not look like what we expect. The challenge is not only to look harder, but to think broader about what evidence of intelligence might mean. And this naturally leads us to the next question. If civilizations on Mars left signals or records, could any of them be remembered here on Earth? Is it possible that myths, legends, or ancient stories on our planet preserve fragments of memory that began not on Earth, but on Mars. When we look at human history, one of the most intriguing patterns is how myths and legends often preserve memories of real events in distorted or symbolic form. Stories of floods, lost lands, and celestial beings appear in cultures separated by vast distances and time. Some of these myths coincide with geological or archaeological evidence, suggesting they are not pure invention, but memory passed through generations. This raises a curious question. Could some of Earth's ancient myths be distant echoes of civilizations that began not here, but on Mars? Around the world, traditions describe origins from the sky. In many indigenous cultures, the first people are said to have descended from above, carried by beings of light or fire. In Mesoamerican mythology, gods are often described as descending from the heavens, bringing knowledge and order to humanity. In ancient Mesopotamia, texts describe those who came from above, teaching agriculture, writing, and governance. These myths are usually interpreted symbolically or as metaphors for natural forces. But what if they carry fragments of something larger? If Martian civilizations once existed, and if they faced collapse, it is not impossible that some of them could have reached Earth. Over thousands of years, their arrival could have been preserved not as history, but as legend, retold until it became myth. The possibility of contact between Mars and Earth is not entirely speculative. We know rocks from Mars have landed on Earth, carried by asteroid impacts that ejected fragments into space. Some scientists suggest microbial life could have traveled this way, seeding Earth in a process known as panspermia. If simple life could make the journey, then theoretically more complex migrations could have occurred. Civilizations on Mars, desperately trying to survive, may have found ways to send themselves or their genetic material through space. Even if their methods were primitive by our standards, over long spans of time, the attempt could succeed. If so, Earth's myths may be distorted memories of these arrivals. Flood myths are another example worth considering. Nearly every culture has a story of a great flood that destroyed early civilizations. In Mesopotamia, it is the flood of Utnapishtim, later reflected in the biblical story of Noah. In South America, there are traditions of floods sent by gods to reset humanity. In India, the story of Manu describes a flood that destroyed everything but a small remnant of life. These stories are so similar that many researchers suggest a common source, perhaps a real event in antiquity that affected all cultures. But what if these myths are not about events on Earth, but about memories brought from outside? Mars lost its atmosphere catastrophically. When its magnetic field collapsed, solar wind began stripping away atmospheric layers. Oceans, if they existed, either evaporated into space or froze beneath the surface. For any civilization on the surface, this would be an apocalypse through water, but in reverse. Not a flood that comes, but waters that leave forever. Oceans disappearing into the sky, rivers turning to dust. If survivors reached Earth and passed these stories down, details could have distorted over millennia. The loss of water became its excess. Desiccation turned into deluge. But the central theme remained: catastrophe through water that ended a former world. Greek myths speak of ages of humanity: golden, silver, bronze. Each era ended with cataclysm, after which few survived to begin again. Hindu cosmology describes cycles of creation and destruction, where civilizations rise and fall in predetermined rhythms. What if these cycles describe not Earth but Mars, a planet that saw multiple eras of stability separated by long periods of decline? Mars has two small moons, Phobos and Deimos. Officially, they are considered captured asteroids, but their orbits raise questions. Phobos orbits Mars faster than the planet rotates around its axis. It rises in the west and sets in the east. Its orbit is almost perfectly circular and lies precisely above Mars's equator. For a captured asteroid, this is unusual. Capture typically results in elliptical, inclined orbits. But Phobos moves as if it were placed there intentionally. In the 1960s, Soviet astrophysicist Yosef Shklovsky suggested Phobos might be hollow, possibly artificial. His calculations were based on anomalous orbital acceleration. This was later explained by tidal forces, but the idea lingered. Phobos is also covered with strange grooves, parallel lines stretching for kilometers. Some are 90 meters deep and 200 wide. They do not resemble typical crater patterns. They look structured, almost organized. One theory suggests these are signs of destruction, fractures from an object slowly breaking apart under gravitational stress. Another proposes impacts from debris of a giant collision on Mars, but some researchers see something different. What if these grooves are not natural? What if Phobos once served purposes we do not yet understand? An ancient civilization could have used its moons as observatories, as refuges, as stations for launching missions into deeper space. If Mars was dying, its moons could be last outposts, places where thin atmosphere did not matter. Missions to Phobos have had a strange history of failures. Soviet Phobos 1 lost contact en route. Phobos 2 reached Mars orbit, but mysteriously fell silent before the final approach phase. Russia's Phobos Grunt in 2011 failed to leave Earth orbit. Coincidence? Probably. Space missions are complex, and failures are common. But the pattern adds intrigue to a moon already full of mysteries. One of the most disturbing clues comes from the Martian atmosphere itself. Mars has an unusually high ratio of xenon, 129, to xenon, 132. This pattern is typical of places that have experienced nuclear reactions. On Earth, we see it near nuclear test sites and reactors. Dr. John Brandenburg, a plasma physicist, proposed a controversial theory. Mars experienced massive nuclear explosions in its past. He points to high concentrations of radioactive elements in certain regions, especially around Cydonia and Utopia Planitia. His hypothesis suggests an ancient Martian civilization was destroyed by nuclear catastrophe, either war or attack from outside. The scientific community remains skeptical. High xenon 129 can be explained by natural processes, intense asteroid bombardment, or volcanic activity. But Brandenburg argues the concentrations are too specific geographically. They form patterns atypical of natural catastrophes, and they coincide with regions where orbital images show the most anomalous formations. If Brandenburg's theory is correct even partially, it rewrites everything. It suggests not just a civilization on Mars, but one that reached a technological level capable of nuclear warfare, or became the target of a force with similar capabilities. This is a desperate idea, but the more missions we send, the more unexplained findings we make. Mars's surface is inhospitable, but what lies beneath it? Radar data from the Mars Express orbiter revealed enormous underground reservoirs, possibly lakes of liquid water hidden beneath the southern polar cap. Other scans discovered extensive systems of lava tubes, natural tunnels formed by ancient lava flows. These tubes can stretch for hundreds of kilometers. They are protected from radiation, dust storms, and extreme temperature fluctuations. For any civilization facing a deteriorating surface environment, going underground would be a logical choice. On Earth, ancient cultures built underground cities. Derinkuyu in Turkey descends 8 levels deep and could shelter 20,000 people. It was built as refuge from invasions and climate hazards. If Martians faced a slowly dying planet, they could do the same, but on a much larger scale. Entire cities could be moved beneath the surface. Generations could live there while the surface became ever more hostile. Over time, these underground civilizations could either fade away or find ways to migrate elsewhere, but their structures would remain. Lava tubes expanded and modified, carved chambers, tunnel systems connecting regions. Current rovers explore only the surface. They cannot penetrate deep. To find traces of underground civilizations, we would need specialized missions. Drills capable of reaching tens of meters deep, or manned expeditions with the ability to explore lava tubes directly. The irony is that the most compelling evidence may be hidden exactly where we have not yet looked. Now let us return to Earth and ask an uncomfortable question. Where did we come from? Evolutionary biology traces human origins through millions of years of development. But there are oddities in our genetics that remain unexplained. The human genome contains so-called junk DNA, sequences that do not code for proteins and whose function remains unclear. Some researchers suggest parts of this DNA could have been inserted, introduced from outside rather than evolved naturally. There is also the question of the rate of human development. From early hominids to modern Homo sapiens took about 6 million years. But the last leap from primitive tools to language, art, architecture, and writing happened surprisingly quickly in geological terms. Around 70,000 years ago, the human population experienced a bottleneck, shrinking perhaps to a few thousand individuals. Genetic analysis shows all modern humans descend from this small group of survivors. After this event, development accelerated. Symbolic thinking flourished. Migrations spread across continents. What caused this bottleneck? The official theory: a massive volcanic eruption of Toba in Indonesia that triggered a volcanic winter. But some data suggests the bottleneck may have preceded the eruption. What if this bottleneck was not just a natural catastrophe, but an arrival? Panspermia suggests life can travel between worlds on meteorites. But what if what arrived was not just microbes, but something more complex? Genetic material, seeds, or even small groups of refugees from a dying planet? If so, our myths about gods descending from the heavens and stellar ancestors may not be metaphors, but distorted stories of real events. Ancient Sumer is one of the most intriguing civilizations in human history. Emerging around 4500 BCE, the Sumerians created the first writing, complex mathematics, astronomical systems, and legal codes. But what sets them apart are their own origin stories. Sumerian texts speak of the Anunnaki, beings who descended from the heavens to create humanity. These beings are described as possessing advanced knowledge, teaching humans agriculture, construction, and sciences. Skeptics note that every ancient culture has myths of creator gods, but Sumerian texts are unusually specific. They describe planets in our solar system with details that should not have been known to ancient observers. One seal, known as VA243, depicts what some researchers interpret as the solar system with an additional planet. Zecharia Sitchin popularized the idea that this planet, named Nibiru, was home to the Anunnaki. The scientific community rejects this interpretation. Astronomers have found no evidence of an additional large planet in the inner solar system. But the idea that ancients knew more about space than we assume deserves consideration. What if the Sumerians received knowledge not from an unknown planet, but from a known one, from Mars? If groups of refugees from Mars reached Earth, they would bring knowledge with them. Astronomical charts, understanding of planetary cycles, memories of their former world. Over millennia, these stories would be mythologized. Real people from another planet would become gods. Technology they used would become magic. But the core of the story would remain: visitors from the sky who gave humanity civilization. Across Earth, ancient structures demonstrate striking similarities despite separation by vast distances and time. Pyramids of Egypt, ziggurats of Mesopotamia, pyramids of Mesoamerica all use similar stepped or triangular forms. Megalithic constructions from Stonehenge to Baalbek and Sacsayhuaman use massive stone blocks precisely cut and fitted without mortar. Traditional archaeology explains this as convergence. Independent cultures arriving at similar solutions. Pyramidal shape is structurally stable. Megalithic construction uses available materials. But some details are harder to explain. The precision of cutting, alignment with astronomical events, mathematical ratios embedded in dimensions. The Great Pyramid at Giza is oriented to true north with accuracy of 3.6 arc minutes. It incorporates the ratio pi and phi, the golden ratio, in its proportions. Its internal chambers align with the constellation Orion. The walls of Sacsayhuaman have blocks weighing up to 200 tons, fitted so tightly a razor blade cannot pass between them. The technology of cutting remains a mystery. What if these structures reflect not independent development, but a shared curriculum. Knowledge transmitted from one source to different cultures. If Martian refugees reached different regions of Earth, they could share basic principles of construction, astronomy, and mathematics. Local cultures adapted these principles, creating variations on a common theme. The result would be structures that look connected, but not identical, exactly what we see. One reason the idea of Martian civilizations seems implausible is the absence of obvious remains, but we underestimate the power of time. Mars lost its atmosphere billions of years ago. Since then, its surface has endured relentless bombardment, cosmic radiation, micrometeorites, dust storms moving at 100 kilometers per hour, and freeze-thaw cycles breaking rocks. On Earth, civilizations disappear within centuries. Mayan cities were swallowed by jungles in 500 years. Roman ruins crumble over 2,000. Even modern concrete begins degrading within decades. A Martian civilization existing 3 billion years ago would leave extremely little. Only the most massive structures, those built on the scale of mountains, would have a chance to leave recognizable shapes. And that is precisely what we may be seeing. Not cities, not roads, but anomalous hills and mountain formations that do not quite fit natural patterns. Critics are right to point out pareidolia makes us see patterns. But there is a difference between seeing a face in clouds and finding geometric ratios in clusters of hills. What is needed is not more speculation, but more data. High-resolution missions targeting specific anomalies, radar scans beneath the surface, analysis of samples from regions with unexplained isotopic signatures. Until that moment, evidence remains circumstantial, but accumulating. Panspermia, the idea that life spreads between worlds, has gained scientific respectability. Microbes can survive in space. Meteorites regularly exchange between Mars and Earth. But what if panspermia works not only at the microbial level? If simple life could make the journey, then theoretically, more complex migrations could occur. Civilizations on Mars, desperately trying to survive, may have found ways to send themselves or their genetic material through space. Even if their methods were primitive by our standards, over long time spans, the attempt could succeed. If so, Earth's myths may be distorted memories of these arrivals. Imagine a civilization knowing its world is dying. It has a century, maybe a millennium to prepare. What does it do? The first instinct is survival in place. Build shelters underground, create enclosed ecosystems, extend life as long as possible. But when it becomes clear the planet will not recover, attention shifts outward to the neighboring planet, to a young blue world with thick atmosphere and oceans, to Earth. The problem is Earth is tens of millions of kilometers away. The journey, even with advanced technology, would take months or years, and a Martian civilization struggling with planetary collapse may not have resources for mass space programs. But there is another way, slower but more reliable: genetic archiving. If you cannot send living beings, you send information to recreate them. DNA is incredibly stable. With proper protection, it can survive millennia in extreme conditions. A Martian civilization could create capsules, tiny protected containers holding genetic material, perhaps even embryos in stasis. Launch thousands of them toward Earth. Most will perish, but a few, just a few, might reach their target. Might land in oceans or on land. Might release their cargo into an environment where it can adapt and thrive. This sounds like science fiction, but it does not contradict physics. We already discussed similar concepts for our own interstellar missions, ideas like generation ships or DNA archives. If such a mission succeeded, the recipients would not remember their origins. After millions of years of evolution on Earth, any connection to Mars would be long lost. But deep in our genetics, imprints might remain, anomalies pointing to intervention. Human evolution has uncomfortable gaps. The missing link between apes and humans, a phrase that persists despite many fossil discoveries. But the problem is not absence of fossils, it is the rate of change. Modern humans appeared about 300,000 years ago, But behaviorally, modern humans, those who made art, symbols, complex tools, emerged only around 70,000 years ago. What triggered this transformation? Some scientists point to genetic mutations, especially in genes linked to speech and cognition. The FOXP2 gene, for example, is critical for language. It differs in humans from other primates by just a few mutations, but these changes occurred relatively recently. What caused these specific mutations exactly then? Even stranger, humans have genes that seem borrowed from other species. About 8% of human DNA came from ancient viruses that embedded themselves in our genome. But there are other sequences whose origin is less clear. Some geneticists suggest horizontal gene transfer, a process common in bacteria where DNA transfers between unrelated organisms. In mammals, this is incredibly rare. Yet it appears to have happened in the human lineage several times. What if some of these genes were not natural acquisitions, but intentional insertions? Not in a laboratory sense, but through the arrival of exogenous genetic material from Mars. This would explain both the speed of human development and genetic oddities that do not quite match expected evolutionary patterns. There is one more connection between Mars and Earth worth exploring: water. Mars once had a huge ocean covering much of the northern hemisphere. Earth has always been a water world. If life moved between planets, it would begin in water. Life on Earth started in oceans about 3.8 billion years ago, roughly the same time Mars still had liquid water on its surface. The window for exchange was open. Microbial mats, stromatolites, and early algae dominated Earth for billions of years. These life forms are incredibly resilient. They can survive in extreme conditions: boiling water, acidic lakes, under dead ice. If Martian life followed a similar path, it too would be aquatic. If samples were sent into space intentionally or accidentally through meteorite impacts, Earth's oceans would be the ideal landing zone. Interestingly, Earth's oceans contain organisms with inexplicably ancient genetic lineages. Some species of microbes seem almost unchanged for billions of years, living fossils at the genetic level. What if these organisms are so old because they did not start here? What if they arrived fully formed from a world where evolution had already been running for millions of years before Earth stabilized? Here is a strange fact. The iron in our blood is the same iron that gives Mars its red color. Hemoglobin, the protein that carries oxygen in our blood, contains iron at its core. When iron oxidizes, it turns red. Blood is red for the same reason Mars is red: iron oxide. Of course, iron is one of the most abundant elements in the universe. It forms in stars and spreads through the galaxy. Every planet in our solar system contains significant amounts of iron. But there is something poetic in the idea that the red pigment in our blood connects us to the red planet. More compelling are specific isotopic ratios. Martian meteorites found on Earth have characteristic isotopic signatures distinguishing them from Earth rocks. If we find similar signatures in ancient Earth organisms, especially those whose origin is unclear, it would be direct evidence of a Martian connection. So far, no such evidence has been found, but we have barely begun to look. Isotopic analysis of fossils is a relatively new field. Most research focuses on species identification rather than tracing planetary signatures. If future studies discover anomalous isotopic ratios in Earth's oldest fossils, it changes everything. Let us return to what we actually know from current missions. The Curiosity rover has been exploring Gale Crater since 2012. It found evidence of an ancient lake that existed for billions of years, long enough for life to begin and develop. Perseverance, arriving in 2021, explores Jezero Crater, site of an ancient river delta. It is collecting samples that will eventually be returned to Earth for detailed analysis. Both rovers have discovered organic molecules, carbon compounds that are building blocks of life. While organic molecules can form non-biologically, their presence in such quantities is intriguing. More intriguing is the discovery of imprints in rock. In 2022, Perseverance photographed a rock formation with patterns strikingly resembling fossilized microbial mats, structures created by colonies of microorganisms on Earth. NASA was cautious with interpretation. Rock formations can mimic biological structures through purely geological processes, but the resemblance is close enough to warrant further investigation. There is also the ongoing mystery of methane. Mars periodically releases plumes of methane into the atmosphere. The source is unknown. On Earth, 90% of methane is produced by living organisms. The remaining 10% comes from geological activity. Mars has no active volcanoes as far as we know. So where is the methane coming from? One possibility is subsurface microbes, still alive deep beneath the surface where conditions are less hostile. Another is ancient biological deposits, slowly decomposing and releasing gas. A third, more ominous, we are detecting remnants of an ancient industrial process. Methane could be a byproduct of technological activity still slowly leaking from sealed underground structures. This is speculative, but it is within what the data allows us to consider. The Japan Aerospace Exploration Agency announced plans to send missions specifically targeting Martian caves and lava tubes within the next decade. These missions will carry drones capable of flying through underground tunnels, equipped with LiDAR scanners and spectrometers to analyze walls, floors, and any formations that appear unusual. If remnants of past civilizations exist, these missions may be our first real chance to find them. But the question remains, what would such remnants look like after billions of years? The answer may be simpler than we think. Not grand ruins or intact cities, but subtle anomalies. Patterns in rock that seem too regular, mineral compositions that do not match surrounding geology, isotopic signatures inconsistent with natural formation, traces of processing, refinement, or deliberate placement. On Earth, archaeologists often discover ancient sites not through visible structures, but through geophysical surveys revealing buried foundations, altered soil chemistry, or unexpected concentrations of certain materials. Mars may require the same approach, searching not for what is visible, but for what is wrong, what does not fit the expected pattern. Consider the possibility that Martian civilizations understood their fate long before it arrived. They may have watched their atmosphere thinning over millennia, measured the loss of magnetic field strength, and calculated how much time remained. In such a scenario, preparation becomes paramount. They might have created archives, buried time capsules, or encoded messages into durable materials designed to outlast geological processes. These archives would not be placed randomly, but in locations chosen for maximum preservation. Deep caverns, polar ice deposits, or sealed chambers beneath layers of rock. The contents could include everything from genetic samples to technological blueprints, cultural records to warnings about what destroyed their world. If we find such archives, they would represent the most profound discovery in human history. Direct communication from another civilization, separated from us by billions of years. But there is another possibility, darker and more unsettling. What if Martian civilizations did not simply fade away? What if they were actively destroyed? Dr. Brandenburg's nuclear hypothesis, while controversial, raises questions that cannot be easily dismissed. The xenon isotope ratios, the concentration of radioactive elements in specific regions, and the apparent scarring of certain landscapes all suggest something catastrophic occurred. Natural explanations exist, but they require coincidences that strain plausibility. If Mars experienced nuclear detonations, we must ask, who was responsible? Was it internal conflict, a civilization destroying itself through war? Or was it external, an attack from beyond Mars itself? The idea of interplanetary warfare seems absurd until we remember that we ourselves have already sent missions to other worlds. A civilization more advanced than ours could easily possess the capability to strike across planetary distances. Some researchers have pointed to anomalies in Mars's orbital characteristics as potential evidence of past violence. The planet's axis is tilted at 25 degrees, similar to Earth's 23.5 degrees. But Mars's axial tilt varies dramatically over time, swinging between 10 and 60 degrees due to lack of a large stabilizing moon like Earth's. This instability affects climate dramatically, creating wild swings between ice ages and warmer periods. Some models suggest Mars's tilt could have been altered by a massive impact or series of impacts in its past. If such impacts were intentional, they would represent weapons of planetary scale, designed to destabilize an entire world's climate and render it uninhabitable. The northern hemisphere of Mars is significantly lower in elevation than the southern hemisphere, a feature called the hemispheric dichotomy. One theory suggests this was caused by an enormous impact early in Mars's history, perhaps the largest impact in the solar system's recorded geology. But the exact nature of this impact remains unclear. Was it a single massive asteroid, multiple impacts over time, or something else entirely? Without more data, we cannot rule out the possibility that Mars's geography itself bears scars of ancient conflict. The moons of Mars continue to be sources of mystery. Phobos, the larger of the two, is only 22 kilometers across, but has features that remain unexplained. Its density is unusually low, about 1.9 grams per cubic centimeter, less than solid rock. This has led some to suggest it may be partially hollow, though the scientific consensus attributes this to porous structure filled with voids. The grooves covering its surface are another puzzle. They radiate from a large crater named Stickney, and the prevailing theory is they are fractures caused by the impact that created Stickney. But some grooves do not align with this pattern. They run in different directions, suggesting multiple formation processes. A few researchers have proposed these could be remnants of surface installations, structures that once covered parts of the moon but have since deteriorated, leaving only foundations carved into the surface. This is highly speculative, but it highlights how little we truly know about objects in our own solar system. Deimos, the smaller moon, orbits farther from Mars and has fewer unusual features, but its origin is equally unclear. Both moons have compositions similar to certain asteroids, supporting the captured asteroid hypothesis. Yet their orbits are too perfect, too circular and equatorial for typical captures. An alternative explanation is that they formed from debris ejected during a massive impact on Mars itself, similar to how Earth's moon may have formed. If this is true, then Phobos and Deimos are pieces of Mars, fragments torn away during a cataclysmic event. Examining them closely could reveal information about Mars's interior composition and history that we cannot easily access from the surface. Future missions to these moons are planned, and what they discover may answer questions we have not yet thought to ask. Returning to Earth, we must address one of the most persistent questions in human biology. Why do we struggle so much with our own planet? Humans are uniquely vulnerable to sunlight compared to many other species. Our skin burns easily, we develop cancers from UV exposure, and we require specific wavelengths of light for vitamin D synthesis. We suffer from chronic back problems due to upright posture, as if our spines were not fully adapted to bipedalism. We have difficulty with childbirth compared to other primates. Our infants are born unusually helpless and dependent, and we require extended childhood development periods. Some researchers have suggested these traits indicate we are not fully adapted to Earth's environment, as if we evolved somewhere with different conditions. Mars, with its lower gravity and different atmospheric composition in the past, would produce different evolutionary pressures. If early humans or their ancestors spent significant time on Mars or carried Martian genetic material, some of these traits could be explained. Lower gravity would reduce stress on spines and joints. Different atmospheric composition might affect skin sensitivity and respiratory development. This is not proof, but it adds to a pattern of oddities that conventional evolution struggles to fully explain. Another biological puzzle is the human brain. Our brains consume 20% of our body's energy despite being only 2% of our body weight. This is extraordinarily inefficient from a survival standpoint. Natural selection typically favors efficiency, yet human brains are energy gluttons. Why would evolution produce such an expensive organ unless the benefits were overwhelming? One answer is that intelligence provided massive survival advantages. But intelligence can develop without such extreme energy demands. Other intelligent species, from dolphins to octopi to crows, have capable brains without the metabolic burden humans carry. What if human brain development was not entirely natural? What if it was accelerated, influenced by genetic material or environmental factors from a civilization that valued intelligence above all else? A Martian civilization facing extinction might prioritize cognitive ability in any survival strategy, embedding genetic sequences that encourage brain development even at metabolic cost. The timing of human brain expansion is also suspicious. About 2 million years ago, the hominin brain began growing rapidly, doubling in size over a relatively short evolutionary period. This coincides roughly with the development of tool use, but correlation does not prove causation. Many species use tools without developing large brains. Something else drove human brain expansion, some selective pressure so intense that it overrode energy efficiency concerns. If genetic material from Mars arrived on Earth during this period, perhaps carried by meteorites or intentionally sent, it could have introduced new sequences that altered developmental patterns. This is speculative genetics, but it is worth noting that horizontal gene transfer, though rare in mammals, does occur and could provide a mechanism for such changes. Human DNA contains sequences that do not appear in other primates, and while most are explained through mutation and selection, some remain mysterious in origin. Let us consider the broader implications of Martian origins for humanity. If we are descendants of Martian life or civilizations, it reframes our place in the universe entirely. We are not unique creations on a special planet, but survivors of a larger story that spans multiple worlds. Our drive to explore space may not be curiosity alone, but genetic memory, an instinct to return to environments our ancestors once knew. The fact that we can imagine living on Mars, that we design habitats and technologies for Martian settlement, may not be innovation, but remembering. Perhaps, somewhere in our collective unconscious, we carry imprints of life under red skies, in caves and domed cities, struggling to survive as a world died around us. This would explain the persistence of certain myths and dreams. The recurring human fantasy of lost golden ages, of paradises that existed before our time, could be distorted memories of Mars during its habitable periods. The universal dream of returning to a homeland, found in nearly every culture's mythology, might not be metaphorical, but literal, a longing for a world our distant ancestors left behind. It would also explain our fascination with Mars, specifically. Among all planets in the solar system, Mars captures human imagination most intensely. Not Venus, despite being closer and more similar in size to Earth. Not Jupiter, despite its grandeur. Not Saturn, despite its beauty. Mars holds a special place in human consciousness, appearing in countless stories, myths, and dreams long before we had telescopes to see it clearly. Ancient cultures associated Mars with war, blood, and transformation. The Egyptians called it Har Decher, the Red One. The Chinese called it the Fire Star. These associations predate scientific understanding of Mars's composition or climate. How did ancient peoples know Mars was significant? Perhaps they did not know intellectually, but remembered viscerally, carrying cultural memory passed down through countless generations from ancestors who actually walked on Martian soil. Modern space exploration may be less about conquest and more about return. When we send rovers to Mars, when we plan human missions, when we design colonies and terraforming strategies, we may be enacting an ancient pattern, a species trying to reclaim what was lost. The urgency behind Mars missions, the emotional investment in making Mars habitable, could stem from something deeper than scientific curiosity or survival instinct. It could be homecoming, an attempt to restore connection to a world that was once ours. If this is true, then successful colonization of Mars would not be humanity's greatest achievement, but its second chance. We would be returning to a world our ancestors abandoned, bringing life back to a place where it once flourished and died. We would be completing a cycle that began billions of years ago, when the first refugees left Mars for Earth, carrying with them hope that someday their descendants might return. This perspective changes everything about how we approach Mars exploration. It is no longer just scientific research or planetary science. It is archaeology on a cosmic scale, excavating our own origins from beneath layers of time and dust. Every mission that lands on Mars is potentially making contact with our past, uncovering evidence of where we truly came from. And every plan to settle Mars is potentially bringing the story full circle, returning life to a world that gave birth to us in forms we can barely imagine now. The evidence for this narrative is circumstantial, built from patterns rather than proof, from mysteries rather than certainties. But the pattern is coherent. Mars was habitable when Earth was not. Mars lost its habitability catastrophically. Earth's myths describe destructions and arrivals from the sky. Human biology has unexplained oddities. Our genetics show signs of rapid change and possible external influence. Ancient civilizations appeared suddenly with advanced knowledge. And throughout history, Mars has held a unique place in human consciousness that transcends its physical characteristics. None of this proves we came from Mars, but it opens the question in ways that demand serious investigation. As we prepare for the next generation of Mars missions, as we develop technologies to drill beneath the surface and explore lava tubes, as we plan to bring samples back to Earth for detailed analysis, we should remain open to possibilities that seem impossible today, but may become obvious tomorrow. The universe is older and stranger than we assume. Life is more resilient and widespread than we once believed, and the story of how we came to be here, on this blue planet, may have chapters we have not yet discovered, written in the rocks and dust of a red world that was our first home. If we know what destroyed Mars, if we can identify the patterns that led to collapse, we can avoid them. We can learn from a civilization that failed and ensure we do not follow the same path. This brings us back to current observations and what they tell us about Mars's fate. The loss of Mars's magnetic field is considered the primary cause of atmospheric collapse. Earth's magnetic field is generated by convection in its liquid iron core, creating a protective bubble that deflects solar wind. Mars once had a similar field, evidenced by magnetic stripes in ancient crustal rocks, remnants of a time when the planet's core was active. About 4 billion years ago, Mars's core cooled and solidified. The magnetic field collapsed, and solar wind began stripping away the atmosphere. Over millions of years, this process transformed Mars from a habitable world into the desert we see today. But why did Mars's core cool so much faster than Earth's? Both planets formed around the same time from similar materials. Earth's core remains molten after 4.5 billion years, while Mars's core solidified in less than a billion. Size is part of the answer. Mars is about half Earth's diameter and has only 11% of Earth's mass. Smaller bodies cool faster because they have less internal heat and greater surface area relative to volume. But some planetary scientists argue size alone cannot fully explain the difference. They suggest Mars may have experienced catastrophic events that accelerated core cooling, perhaps massive impacts that disrupted internal heat distribution or removed significant portions of the mantle. If Brandenburg's nuclear hypothesis has any validity, widespread nuclear detonations on or near Mars could have affected the planet's interior. Nuclear explosions generate electromagnetic pulses and release enormous energy. If detonations occurred at sufficient scale and depth, they could theoretically interfere with core convection, accelerating cooling. This is highly speculative and not part of mainstream planetary science, but it illustrates how catastrophic events on the surface could have consequences for deep planetary processes. Another possibility involves external interference. If a civilization with advanced technology wanted to destroy Mars, targeting its magnetic field would be efficient. Without magnetic protection, solar wind would do the rest of the work, slowly but inevitably stripping away atmosphere and making the surface uninhabitable. This method would be difficult to detect billions of years later, leaving only the result: a dead planet with no obvious cause of death. It is an uncomfortable thought, but one we cannot dismiss without more evidence. What we do know with certainty is that Mars's transformation from habitable to barren was gradual, occurring over hundreds of millions of years. This timeline has profound implications for any civilizations that may have existed there. They would have had warning. They would have watched their world dying slowly. The Japan Aerospace Exploration Agency announced plans to send missions specifically targeting Martian caves and lava tubes within the next decade. These missions will carry drones capable of flying through underground tunnels, equipped with LiDAR scanners and spectrometers to analyze walls, floors, and any formations that appear unusual. If remnants of past civilizations exist, these missions may be our first real chance to find them. But the question remains, what would such remnants look like after billions of years? The answer may be simpler than we think. Not grand ruins or intact cities, but subtle anomalies. Patterns in rock that seem too regular, mineral compositions that do not match surrounding geology, isotopic signatures inconsistent with natural formation, traces of processing, refinement, or deliberate placement. On Earth, archaeologists often discover ancient sites not through visible structures, but through geophysical surveys revealing buried foundations, altered soil chemistry, or unexpected concentrations of certain materials. Mars may require the same approach, searching not for what is visible, but for what is wrong, what does not fit the expected pattern. Consider the possibility that Martian civilizations understood their fate long before it arrived. They may have watched their atmosphere thinning over millennia, measured the loss of magnetic field strength, and calculated how much time remained. In such a scenario, preparation becomes paramount. They might have created archives, buried time capsules, or encoded messages into durable materials designed to outlast geological processes. These archives would not be placed randomly, but in locations chosen for maximum preservation. Deep caverns, polar ice deposits, or sealed chambers beneath layers of rock. The contents could include everything from genetic samples to technological blueprints, cultural records to warnings about what destroyed their world. If we find such archives, they would represent the most profound discovery in human history. Direct communication from another civilization, separated from us by billions of years. But there is another possibility, darker and more unsettling. What if Martian civilizations did not simply fade away? What if they were actively destroyed? Dr. Brandenburg's nuclear hypothesis, while controversial, raises questions that cannot be easily dismissed. The xenon isotope ratios, the concentration of radioactive elements in specific regions, and the apparent scarring of certain landscapes all suggest something catastrophic occurred. Natural explanations exist, but they require coincidences that strain plausibility. If Mars experienced nuclear detonations, we must ask who was responsible. Was it internal conflict, a civilization destroying itself through war? Or was it external, an attack from beyond Mars itself? The idea of interplanetary warfare seems absurd until we remember that we ourselves have already sent missions to other worlds. A civilization more advanced than ours could easily possess the capability to strike across planetary distances. Some researchers have pointed to anomalies in Mars's orbital characteristics as potential evidence of past violence. The planet's axis is tilted at 25 degrees, similar to Earth's 23.5 degrees. But Mars's axial tilt varies dramatically over time, swinging between 10 and 60 degrees due to lack of a large, stabilizing moon like Earth's. This instability affects climate dramatically, creating wild swings between ice ages and warmer periods. Some models suggest Mars's tilt could have been altered by a massive impact or series of impacts in its past. If such impacts were intentional, they would represent weapons of planetary scale, designed to destabilize an entire world's climate and render it uninhabitable. The northern hemisphere of Mars is significantly lower in elevation than the southern hemisphere, a feature called the hemispheric dichotomy. One theory suggests this was caused by an enormous impact early in Mars's history, perhaps the largest impact in the solar system's recorded geology. But the exact nature of this impact remains unclear. Was it a single massive asteroid, multiple impacts over time, or something else entirely? Without more data, we cannot rule out the possibility that Mars's geography itself bears scars of ancient conflict. The moons of Mars continue to be sources of mystery. Phobos, the larger of the two, is only 22 kilometers across, but has features that remain unexplained. Its density is unusually low, about 1.9 grams per cubic centimeter, less than solid rock. This has led some to suggest it may be partially hollow, though the scientific consensus attributes this to porous structure filled with voids. The grooves covering its surface are another puzzle. They radiate from a large crater named Stickney, and the prevailing theory is they are fractures caused by the impact that created Stickney. But some grooves do not align with this pattern. They run in different directions, suggesting multiple formation processes. A few researchers have proposed these could be remnants of surface installations, structures that once covered parts of the moon but have since deteriorated, leaving only foundations carved into the surface. This is highly speculative, but it highlights how little we truly know about objects in our own solar system. Deimos, the smaller moon, orbits farther from Mars and has fewer unusual features, but its origin is equally unclear. Both moons have compositions similar to certain asteroids, supporting the captured asteroid hypothesis. Yet their orbits are too perfect, too circular and equatorial for typical captures. An alternative explanation is that they formed from debris ejected during a massive impact on Mars itself, similar to how Earth's moon may have formed. If this is true, then Phobos and Deimos are pieces of Mars, fragments torn away during a cataclysmic event. Examining them closely could reveal information about Mars's interior composition and history that we cannot easily access from the surface. Future missions to these moons are planned, and what they discover may answer questions we have not yet thought to ask. Returning to Earth, we must address one of the most persistent questions in human biology. Why do we struggle so much with our own planet? Humans are uniquely vulnerable to sunlight compared to many other species. Our skin burns easily, we develop cancers from UV exposure, and we require specific wavelengths of light for vitamin D synthesis. We suffer from chronic back problems due to upright posture, as if our spines were not fully adapted to bipedalism. We have difficulty with childbirth compared to other primates. Our infants are born unusually helpless and dependent, and we require extended childhood development periods. Some researchers have suggested these traits indicate we are not fully adapted to Earth's environment, as if we evolved somewhere with different conditions. Mars, with its lower gravity and different atmospheric composition in the past, would produce different evolutionary pressures. If early humans or their ancestors spent significant time on Mars or carried Martian genetic material, some of these traits could be explained. Lower gravity would reduce stress on spines and joints. Different atmospheric composition might affect skin sensitivity and respiratory development. This is not proof, but it adds to a pattern of oddities that conventional evolution struggles to fully explain. Another biological puzzle is the human brain. Our brains consume 20% of our body's energy despite being only 2% of our body weight. This is extraordinarily inefficient from a survival standpoint. Natural selection typically favors efficiency, yet human brains are energy gluttons. Why would evolution produce such an expensive organ unless the benefits were overwhelming? One answer is that intelligence provided massive survival advantages. But intelligence can develop without such extreme energy demands. Other intelligent species, from dolphins to octopi to crows, have capable brains without the metabolic burden humans carry. What if human brain development was not entirely natural? What if it was accelerated, influenced by genetic material or environmental factors from a civilization that valued intelligence above all else? A Martian civilization facing extinction might prioritize cognitive ability in any survival strategy, embedding genetic sequences that encourage brain development even at metabolic cost. The timing of human brain expansion is also suspicious. About 2 million years ago, the hominin brain began growing rapidly, doubling in size over a relatively short evolutionary period. This coincides roughly with the development of tool use, but correlation does not prove causation. Many species use tools without developing large brains. Something else drove human brain expansion, some selective pressure so intense that it overrode energy efficiency concerns. If genetic material from Mars arrived on Earth during this period, perhaps carried by meteorites or intentionally sent, it could have introduced new sequences that altered developmental patterns. This is speculative genetics, but it is worth noting that horizontal gene transfer, though rare in mammals, does occur and could provide a mechanism for such changes. Human DNA contains sequences that do not appear in other primates, and while most are explained through mutation and selection, some remain mysterious in origin. Let us consider the broader implications of Martian origins for humanity. If we are descendants of Martian life or civilizations, it reframes our place in the universe entirely. We are not unique creations on a special planet, but survivors of a larger story that spans multiple worlds. Our drive to explore space may not be curiosity alone, but genetic memory, an instinct to return to environments our ancestors once knew. The fact that we can imagine living on Mars, that we design habitats and technologies for Martian settlement, may not be innovation, but remembering. Perhaps somewhere in our collective unconscious, we carry imprints of life under red skies, in caves and domed cities, struggling to survive as a world died around us. This would explain the persistence of certain myths and dreams. The recurring human fantasy of lost golden ages, of paradises that existed before our time, could be distorted memories of Mars during its habitable periods. The universal dream of returning to a homeland, found in nearly every culture's mythology, might not be metaphorical but literal, a longing for a world our distant ancestors left behind. It would also explain our fascination with Mars specifically. Among all planets in the solar system, Mars captures human imagination most intensely. Not Venus, despite being closer and more similar in size to Earth. Not Jupiter, despite its grandeur. Not Saturn, despite its beauty. Mars holds a special place in human consciousness, appearing in countless stories, myths, and dreams long before we had telescopes to see it clearly. Ancient cultures associated Mars with war, blood, and transformation. The Egyptians called it Har-Detcher, the Red One. The Chinese called it the Fire Star. These associations predate scientific understanding of Mars's composition or climate. How did ancient peoples know Mars was significant? Perhaps they did not know intellectually but remembered viscerally, carrying cultural memory passed down through countless generations from ancestors who actually walked on Martian soil. Modern space exploration may be less about conquest and more about return. When we send rovers to Mars, when we plan human missions, when we design colonies and terraforming strategies, we may be enacting an ancient pattern, a species trying to reclaim what was lost. The urgency behind Mars missions, the emotional investment in making Mars habitable, could stem from something deeper than scientific curiosity or survival instinct. It could be homecoming, an attempt to restore connection to a world that was once ours. If this is true, then successful colonization of Mars would not be humanity's greatest achievement, but its second chance. We would be returning to a world our ancestors abandoned, bringing life back to a place where it once flourished and died. We would be completing a cycle that began billions of years ago, when the first refugees left Mars for Earth, carrying with them hope that someday their descendants might return. This perspective changes everything about how we approach Mars exploration. It is no longer just scientific research or planetary science. It is archaeology on a cosmic scale, excavating our own origins from beneath layers of time and dust. Every mission that lands on Mars is potentially making contact with our past, uncovering evidence of where we truly came from. And every plan to settle Mars is potentially bringing the story full circle, returning life to a world that gave birth to us in forms we can barely imagine now. The evidence for this narrative is circumstantial, built from patterns rather than proof, from mysteries rather than certainties. But the pattern is coherent. Mars was habitable when Earth was not. Mars lost its habitability catastrophically. Earth's myths describe destructions and arrivals from the sky. Human biology has unexplained oddities. Our genetics show signs of rapid change and possible external influence. Ancient civilizations appeared suddenly with advanced knowledge. And throughout history, Mars has held a unique place in human consciousness that transcends its physical characteristics. None of this proves we came from Mars, but it opens the question in ways that demand serious investigation. As we prepare for the next generation of Mars missions, as we develop technologies to drill beneath the surface and explore lava tubes, as we plan to bring samples back to Earth for detailed analysis, we should remain open to possibilities that seem impossible today, but may become obvious tomorrow. The universe is older and stranger than we assume. Life is more resilient and widespread than we once believed. And the story of how we came to be here, on this blue planet, may have chapters we have not yet discovered, written in the rocks and dust of a red world that was our first home. Now pause for a moment and consider what this means for the future. If we are correct, if Mars truly was the origin point for life that eventually became humanity, then our current trajectory is not random. We are being pulled back by forces deeper than curiosity, older than memory, as inevitable as gravity itself. But there is more to this story, evidence we have not yet discussed, clues hidden not on Mars or Earth, but in the space between them, and in observations that challenge our understanding of what is possible in our solar system. The asteroid belt between Mars and Jupiter has long been considered debris from a planet that never formed, material prevented from coalescing by Jupiter's gravitational influence. This is the standard model, and it fits most observations. But there are anomalies in the asteroid belt that raise questions. Some asteroids have compositions inconsistent with primordial formation. They show signs of differentiation, where heavier elements sank to a core, while lighter materials formed a crust, a process that occurs in full planets but should not happen in small asteroids that never had sufficient heat or pressure. The presence of differentiated asteroids suggests they are fragments of larger bodies that once existed and were destroyed. Could one of these larger bodies have been a planet? The idea of a fifth planet between Mars and Jupiter appears in various astronomical theories over the centuries. Johannes Kepler noted the large gap in planetary spacing and suggested something should be there. The Titius-Bode law, an empirical formula describing planetary orbits, predicts a planet at the asteroid belt's location. While this law is not considered physical law but rather mathematical curiosity, the prediction is striking. If a planet once existed there and was destroyed, what could cause such destruction? Natural processes can break apart small bodies through collisions or tidal forces, but destroying an entire planet requires energy on scales difficult to imagine. Gravitational disruption from Jupiter is insufficient. Even a massive impact would shatter a planet into large fragments rather than reducing it to asteroids. Some researchers have suggested internal instability, perhaps runaway nuclear reactions in the core. But this requires planetary compositions and conditions we have no evidence existed. Another possibility, one that seems impossible but must be mentioned, is intentional destruction. If intelligent life existed in our solar system billions of years ago, if conflicts arose between worlds or civilizations, then planet-scale weapons may have been developed. This sounds like science fiction. But we must remember that we ourselves have developed weapons capable of destroying our own civilization. Given enough time and desperation, what might we develop next? If Martian civilizations faced threats from beyond Mars, if they competed with other worlds for resources or survival, then weaponry capable of planetary destruction is not inconceivable. There is a fragment of evidence that supports this uncomfortable idea. In 1972, astronomer Tom Van Flandern proposed the exploded planet hypothesis, based on anomalies in cometary orbits. He argued that many comets show trajectories suggesting they originated from a specific region of the asteroid belt and were ejected during a catastrophic event about 3 million years ago. While mainstream astronomy has not widely accepted this theory, Van Flandern's calculations were mathematically sound. If a planet was destroyed in relatively recent geological time, it would explain certain orbital characteristics we observe today. It would also suggest that catastrophic events in our solar system are not restricted to the distant past, but can occur even in epochs when Earth already had complex life. This raises the disturbing question: could it happen again? Are there forces or civilizations in our solar system or nearby space that pose threats we do not yet recognize? Consider also the Kuiper Belt and Oort cloud, regions of icy bodies beyond Neptune. These regions contain millions of objects, most of which are considered primordial remnants from the solar system's formation. But some objects have unusual characteristics. Oumuamua, the interstellar visitor that passed through our solar system in 2017, accelerated in ways that could not be fully explained by outgassing or gravitational interactions. Some scientists suggested it might be artificial, perhaps a probe or derelict spacecraft. While this interpretation remains controversial, it demonstrates that our solar system receives visitors from beyond, objects whose origins and nature we cannot always determine. If one interstellar object can be potentially artificial, then others might be as well. The Kuiper Belt and Oort cloud could contain not only natural debris, but remnants of ancient exploration, perhaps missions launched millions of years ago by civilizations that no longer exist. Mars itself may have been part of a larger network, not an isolated world, but one node in a system of inhabited or monitored planets. If civilizations arose on Mars, they would eventually notice Earth. From Mars, Earth would appear as a brilliant blue star, the third brightest object in the sky after the Sun and Venus. A Martian civilization with even basic astronomy would recognize Earth as potentially habitable. They would see its thick atmosphere, detect oxygen and water vapor, and understand it could support life. If Mars was dying, Earth would be the obvious destination, the nearest refuge, the only other world in the solar system where survival was possible. This is where the story becomes not just about origins, but about intention. If Martians reached Earth, they did so deliberately. They chose Earth. They navigated across tens of millions of kilometers of space, survived the journey, and established themselves in an alien environment. This was not accident or panspermia's random drifting of microbes. This was migration, exodus, perhaps the greatest journey any civilization has ever attempted. How would such a journey be possible? Mars, even at its peak, likely did not have technology matching modern human capabilities. But they would not need advanced spacecraft to accomplish this. There is a mechanism called a Hohmann transfer orbit, a fuel-efficient path between two planets that uses gravitational dynamics to minimize energy requirements. With basic rocketry and understanding of orbital mechanics, a civilization could launch vessels from Mars to Earth. The journey would take months, and survival during transit would be the greatest challenge. But if Martian biology was more resilient than ours, if they could endure radiation and hibernation, or if they sent genetic material rather than living beings, the journey becomes feasible. Imagine capsules launched from Mars, hundreds or thousands of them, each containing preserved genetic material, perhaps embryos in stasis, perhaps even hibernating adults. Most would fail, destroyed by radiation, collisions, or equipment failure. But a few, just a few, might reach Earth. They might land in oceans where water cushioned impact. They might be recovered by whatever life already existed on Earth, or simply released their contents into environments where evolution could take over. This process would not create humans immediately. It would introduce Martian genetic material into Earth's biosphere, where it would mix with native life through various mechanisms. Over millions of years, this material would be refined, selected, and integrated. The result would be hybrid life, organisms carrying genetic information from two worlds. Eventually, some of these organisms would develop intelligence, consciousness, and culture. They would become us, never knowing they carried within them the legacy of a dead planet and a lost civilization. The beauty of this scenario is that it does not require conspiracy or hidden evidence. It requires only time and the natural processes of genetics and evolution. If Martian material arrived on Earth 3 billion years ago, no trace of the original arrival would remain. Everything would be erased except the genetic signatures, and those would be nearly impossible to distinguish from natural mutation without knowing exactly what to look for. But perhaps they left more than genetics. Perhaps they left instructions, encoded not in stone or metal but in DNA itself. Our genome contains vast stretches of non-coding DNA, sequences that do not produce proteins and whose purpose remains unclear. Some of this DNA is regulatory, controlling when and how genes activate, but much of it has no known function. What if hidden within these sequences are patterns, information encoded in the base pairs of adenine, thymine, guanine, and cytosine? DNA is a remarkably efficient information storage system. 1 gram of DNA can theoretically store 215 petabytes of data. If a civilization wanted to preserve knowledge across billions of years and through the unpredictability of evolution, embedding it in genetic code would be the most durable method imaginable. The information would be copied with every cell division, passed to every offspring, distributed throughout an entire species. It could not be lost unless the species itself went extinct. Decoding such information would require recognizing it exists, a challenge when we assume all genetic material is natural. But if we began searching for patterns in non-coding DNA that resemble artificial construction, mathematical sequences, or linguistic structures, we might find surprises. Some researchers have already noticed that certain genetic sequences show patterns resembling mathematical constants or geometric ratios. These are usually explained as coincidences or byproducts of natural selection, but they deserve closer examination. If even one sequence were confirmed as artificially constructed, it would prove that intelligence has manipulated Earth's biosphere at a genetic level. This would not tell us whether that intelligence was Martian, terrestrial, or something else entirely, but it would confirm that human origins involve more than random mutation and natural selection. It would mean we were designed, at least in part, and that design carries a message we have not yet learned to read. The implications extend beyond our past to our future. If we carry Martian genetics, if we are products of a deliberate seeding or migration, then our destiny may not be confined to Earth. We may be called to return to Mars not by ambition, but by something deeper, a biological or psychological imperative built into us from the beginning. This could explain the persistence of space exploration despite enormous costs and frequent setbacks. It could explain why we continue planning Mars missions even when resources could be used to solve problems here on Earth. Something drives us outward, and that something may be older than human civilization itself, embedded in our biology by ancestors who knew their survival depended on reaching other worlds. If this is true, then settling Mars is not conquering a new frontier but fulfilling our original purpose, completing a journey that began when the first refugees left Mars for Earth. We would be returning home, bringing life back to a world that gave birth to us in forms we no longer remember. But there is a darker side to this possibility, one we must confront honestly. If Mars was home to civilizations that destroyed themselves or were destroyed by others, then we may carry not only their genetics, but their flaws. The conflicts that ended Martian civilizations could be encoded in us as aggression, tribalism, or self-destructive tendencies. We see these patterns throughout human history: wars, genocides, environmental destruction, nuclear weapons. Are these uniquely human failings, or are they inherited from Martian ancestors who made the same mistakes? If we return to Mars carrying the same flaws that destroyed it once, we risk repeating the cycle. This is why understanding our origins matters. It is not just about satisfying curiosity or answering philosophical questions. It is about survival. If we know what destroyed Mars, if we can identify the patterns that led to collapse, we can avoid them. We can learn from a civilization that failed and ensure we do not follow the same path. This brings us back to current observations and what they tell us about Mars's fate. The loss of Mars's magnetic field is considered the primary cause of atmospheric collapse. Earth's magnetic field is generated by convection in its liquid iron core, creating a protective bubble that deflects solar wind. Mars once had a similar field, evidenced by magnetic stripes in ancient crustal rocks, remnants of a time when the planet's core was active. About 4 billion years ago, Mars's core cooled and solidified. The magnetic field collapsed, and solar wind began stripping away the atmosphere. Over millions of years, this process transformed Mars from a habitable world into the desert we see today. The missions we send today are not just scientific expeditions. They are searches for answers to the most profound questions humanity has ever faced. Who are we? Where did we come from? Are we alone, or are we the continuation of something far older? Each sample returned from Mars, each image captured by rovers, each measurement taken by orbiters brings us closer to truth. And when that truth finally emerges, whether it confirms our Martian origins or reveals something entirely unexpected, it will change forever how we see ourselves and our place in the cosmos. Until then, we continue searching, driven by questions that may be older than human civilization itself, following paths that lead us back to a red planet that may hold the key to understanding not just where we came from, but where we are going. The story of Mars and Earth may be unfinished, a narrative still being written with each mission we launch and each discovery we make. And perhaps, someday, when humans finally walk on Martian soil and explore the depths of its ancient lava tubes, we will find not just evidence of past life, but evidence of ourselves, written in stone and dust, waiting billions of years to be recognized. The journey continues, the questions remain, and Mars, silent and patient, keeps its secrets still, waiting for the day when its children return to remember what was forgotten and reclaim what was lost. Good night.